the common gate stage. So here we have again the concept, the unity gain current amplifier. That was the concept, and here it's even maybe more difficult to see that there is feedback. But we will see this. We will evaluate the loop for this one as well. So here you see the implementation with the transistor, the common gate, and we know the properties. We can say this will be the properties because it's a non-energetic feedback stage. So it has D equals unity because it's a current follower, and A, B, C cannot be affected by feedback because there's no feedback. There's only feedback for D, current to current. It is current sensing at the load and current comparison at the source. So only D is affected by negative feedback. It is non-inverting because we take the current the other way around as in the common source stage, and we took the current, the input current is the other way around as from the current common source stage. So we have input parallel, shunt feedback, current comparison, and at the output, we have series feedback or current sensing. That are the keywords to generate such structures. So let's now study the behaviors with the behavioral modifications with respect to the CE stage that are a result of negative feedback. So non-energetic feedback, we know non-energetic feedback, the equivalent input noise sources of the common gate state must be equal to those of the DCS stage. It doesn't need any calculation because the class, thinking classes, the class of non-energetic feedback amplifiers have this property, and this is a member of the class. So all members have this property. That makes it simple. As the CD stage was also a member of this class. The drive capability, energy storage, and power efficiency, same story. Equal as those of the CS stage because there's no energy storage, no power dissipation, and no losses in the feedback network. Of course, the amount of feedback, again, is expressed by the loop gain. So we can make, as with the CD stage, the feedback very ineffective. And how can we make it ineffective here? Well, by having no possibility for current comparison. How would you do that? Well, short the input, drive it from zero, drive it from a voltage source, or by leaving the output open, because then there can be no current sensing because there's no current. So if terminated with a relatively high input impedance or left open, the output series feedback is not effective. We cannot sense the current because the loop is broke. And the input impedance approximates that of the CS stage. And if we drive it from a low impedance or the input is shorted, then the parallel comparison is not effective, as I told you before, and the output impedance approximates that of the CS stage. So exactly the same story, but dual. Let's say replace current with voltage, and you have the story from the CD stage and the CG stage. Now let's look at the ideal gain and the asymptotic gain of this stage. Oops, sorry. Here we have the controller, and one part of the controller I've taken out, but now at the output, you see the drain bulk capacitance is part of the controller, it's inside here, but it's, you know, it complicates a little bit the calculations for the asymptotic gain. So that's why I took it out. And now you see if I calculate the ideal gain, by the way, then the whole controller, including this capacitor, that is maybe a little bit confusing in the drawing. So I have to think of maybe making a different drawing for this. So the whole controller, including this capacitor, is replaced with a nuller. And then we have this schematic that we already saw, and the gain is unity. And here must be this sentence probably again, because I copied it. The gain, if the loop gain reference is replaced with a nuller. So that is only the controlled source. All other elements just stay in. If the loop gain reference is placed with a nuller, that means that replaced with a nuller, that means that you can generate any current with this controlled source without needing any voltage for it because its gain becomes infinite. That's what it says. And that means that at the input, there is no current flowing. So here you see then the asymptotic gain of the story, and you see basically the current division that is present here. The loop gain equivalent circuit, well, again, you select a reference variable, which is now GM plus GMB. They operate together. They are in parallel because VGS is the same as G bulk B source. So it's basically controlled by two controlled sources. Now we have more loop gain thanks to the backgate effect. So you can simplify this one as well, of course, and have this, including all the, parallel connections, and our assumption that if the load impedance becomes infinite, that there's no loop gain, you clearly see. If you make RL infinite and CL 0, there's no loop and there's no loop gain. And if you short the source, then RS equals 0 or the total capacitance is infinite, then there's also no loop gain. So the loop gain strongly depends, or strongly, it depends on the load impedance and of the source impedance, of course. So, and RO establishes a direct transfer. Now, this is what I already discussed. The loop gain drops under the conditions of this impedances. So that is basically the whole behavior of the CG stage. And let's have a look now on its bandwidth and stability as we did with the common drain stage. So for the bandwidth and the stability, we need the DC loop gain and the pole. So the DC loop gain we can calculate here, and the maximum DC loop gain that can be achieved here is larger because of the backgate effect, because it helps. The two control sources are basically in parallel. So N is the substrate factor and mu is the voltage gain factor of the FET. So N times mu. We have two poles. I didn't ask you now, but I just say we have two poles. We have two independent capacitor voltages. There's no loops of capacitors. But look, we also have 1, 0. And the 0 in the loop gain is at, if there is an RO, if RO is infinite, then the 0 and the pole are on the same frequency because there's two poles in it. And if there is a, let's say, let's make RO 0 infinite, then you see that the voltage VI is completely found from one pole and IC. But there is another pole in the circuit. This you cannot ignore. So there must be a 0 on top of this pole to make it ineffective. So if RO goes to infinity, the 0 that is in the loop coincides with one pole, and we have a single pole transfer. That is here, the conclusion. Of course, it is, well, that's okay. So this is often the case in practical situations, by the way. So we will see this. And then the bandwidth is omega t, and it's a first order system. So when the CG stage is driven from a high impedance and terminated with relatively low impedance, and RO is quite a large impedance if you have a good FET. So that means the load is quickly, you have already this effect. So it means you have just a single pole system, just omega t. I didn't make any demonstration file from this one with the Jupyter notebook. You are welcome to do so and to check the conclusions, to do it yourself. Play with the other one. The other one is downloadable from the website. So this is what I wanted to tell about the common gate stage.